Hi everybody! In this video I would like to create a simple and effective shader that can significantly change the appearance of a selected sprite or even the entire screen. The effect you are seeing now can certainly have many uses, such as disabling a specific UI element or simulating an image in an old newspaper article. Let's do it! Okay, so as usual, I'm working in Godot engine. However, the shader we create in this video should be usable almost anywhere, because we'll be using only standard operations such as dot product, trigonometric functions or matrix vector multiplication. So, just like the last time, I'll start by creating a new 2D scene. I'll do it here, right click, create new scene, and let's call it dot matrix. Okay, and again I'll choose a screenshot from our upcoming game because it seemed pretty suitable for this purpose. It's right here. I'll just drag it there to create the sprite 2D node, and let's open it in the inspector and fix the transformation. I think we can set it to 0, and in the offset disable centered. Now it's perfectly aligned. Very well. So we need a new material on this sprite node as a shader material. Let's do it here, material, new shader material, click and create a new shader, which must be canvas item. This is correct, and I'll put it to the shaders folder. Okay, and create and click to open it in the shader editor. Very well, so we'll delete what we don't need, leaving only the fragment function. Let's expand that a bit and do this, deleting the vertex function and light function. Okay, at this point I usually define the resolution we will use to recalculate the aspect ratio, because we are not working with a square but with a rectangle. This time, however, we'll apply the shader to a specific image, just this node. So we can easily calculate the resolution using the internal variable texture pixel size. I will write this basic fragment function body. So that would be vector2 resolution is 1 divided by the mentioned textured pixel size. Great. So in order to display something, it is necessary to read the value of the current pixel of the texture, perform some transformations and use the result as the output for the final color of the pixel. Therefore, we will add the display of such a pixel for now without any additional changes. So first we need to read the pixel color. Vector3 color would be the function texture applied on the current texture and the current UV coordinates, and RGB components, because we are working with vector3 only. And we need to assign the result to the internal variable color, which is vector4. So we would have first 3 components as our color, and the last one is alpha set to 1. So as you have surely noticed, I'm only using the first 3 components of the color, and I'm setting the alpha channel to 1 by default. This is because the final effect does not account for any transparency, so whatever comes from the source texture, we will adjust it this way. Okay, so how do we achieve the desired effect? The dot effect is created using shades of gray, so it will be necessary to calculate such a value for each pixel. To do this, we will use a so-called luminance vector, which you may remember from the previous video when we performed color saturation. The luminance vector adjusts the shades of gray to the human eye, which reacts differently to various colors. This time We will not use it as a constant, but add the vector as a uniform parameter so that we can later change its value for further tweaking. I will do it here at the top, so it will be uniform vector 3 luminance and use source color as a hint, so we will get this nice color picker in the inspector, and the initial value, let's set to these values 3086.6094 and finally 0.0820. Okay, if you're interested in the origin of these values, please take a look at the previous video about the color adjustment or brightness, contrast, saturation. I explained where it came from. Anyway, so how do we use it? The simplest way is usually to calculate the dot product of the current color and the luminance vector, like this. I will add one more line here. Float, let's call it gray, would be the dot product of dimensions, components, color and luminance. Great. We still don't see anything displayed. Let's add one more line where we use the obtain grayscale value for the color vector. So the color would be changed to vector 3 of gray, which means simply that all three components of the vector 3 would be the same, this float value gray, and we can already see some result. The original picture has been turned to grayscale. This is not bad, except that we have a grayscale image but without the main feature, the dots. It's time to implement a function which we will call dot matrix. Let's start with a simple version which takes UV coordinates and input parameter as input parameters and returns the sign of UVX, which should correspond to vertical lines. Let's do it. The function would return float. It's called dot matrix, and as I said, it takes UV coordinates as the input parameter and returns at this moment just sign of UVX and semicolon. And let's what's wrong? Sorry, no, vector 1, vector 2, of course. And of course we will add the result of this function to the grayscale value that we have in the fragment function. So instead of just gray, we would add dot matrix of UV. Let's wait for it. Okay, something is happening, but we are still not quite there, right? We forgot about the resolution, which we'll now add to the calculation. So let's get back where it is here, and instead of UV, it must be multiplied by the resolution vector. Okay, now we can at least see those vertical stripes. However, it seems to me that the colors are a bit strange, too bright and not contrasty enough. So before we proceed further, let's add adjustable contrast and brightness to our code as new uniform parameters. Uniform float brightness with a hint range from 0.1 to, let's say, 20, and the step would be 0.1. Let's set the initial default value to 2, and for the, oh no, I think it should be 0.01. Okay, and for brightness and for the contrast, again, uniform float contrast with a hint range from from 1 to 4, and again step 0.01. Initial value would be set to 2 as well. Great. And we will use these values in the fragment function, which means first we will multiply the dot product by the contrast, and we need brightness somewhere here in the final color, multiply by brightness, Is it better? Maybe a bit, but we are still not there, of course. The dot matrix function returns too high of a value, so let's try to reduce the result a bit, maybe by 1, -1. Okay, finally we achieved something usable. Usable, not exactly, but it returns some result. We can, if we wanted to horizontal stripes instead of the vertical ones, we would simply apply the sign to UVY. Let's try it. Okay, here it is. And of course we need dots, not stripes. So we can achieve that by multiplying the sign of both UV vector components. So we have UVY here and sign UVX multiplied by that. Okay, some dots are finally there. So we have the basic version of the effect already. When we enlarge the image, we can clearly see how it is constructed. Yeah, the dots are there. In the inspector, we can change the brightness and contrast and see what happens. Here in the shader parameters, let's try something. Increase the brightness, increase the contrast, yeah, or let's play with the luminance, try some other shades. Yeah, definitely it's getting somewhere. Good. Fine, let's revert the original default values. Okay, but as I said, this is a basic algorithm. If, for example, we wanted to experiment with the pattern of these dots themselves, currently we can't do anything. Let's add 2 more uniform parameters for scaling and a rotation. So again, I'll move it there and add it here. Okay, uniform float scale with a hint range from 0 to 2 and a step 0.01 starting at 1 and uniform float angle and range from 0 to, let's try 2 pi, and since we cannot use the built-in constants here, I will just write 6.28, which is an approximative value of 2 pi with the same step, and let's start at 3. Alright, and we'll use them in the dot matrix function. So for rotation, first we'll create a rotation matrix just like in the previous video. I'll do it here. mat2, let's call it rotate with the parameter a as angle, and first let's define this value sine a and the same for cosine a. CA cosine A, and we want to return the matrix that is used for calculating the rotation. It would be vector 2 of sine A and cosine A and sine A, and vector 2 of negative sine A and cosine A, and semicolon, of course. And here. Okay, so this is the rotation matrix. Let's apply it in the dot matrix function. So we will define another vector 2, let's call it rot UV, like rotated UV coordinates, and it contains the result of the rotate function with angle, which is the uniform parameter defined here, and it should be multiplied by the UV coordinates, of course, and multiplied by scale. And of course we must not forget to replace UV here by the rotated UV. Let's do it now. UV UVY, and there we go. I would say that we are done with the shader. Let's try changing different parameters and see what happens. So for example, the scale, yeah, it's moving. Now it gives us bigger dots, so it can be a completely different effect, especially if we change the angle. Can you see how it's rotating? So with these tweaks we can set up any kind of effect of this kind we are interested in: brightness, contrast, or maybe the original scale was better, even to the other side. Yeah, definitely many opportunities and many combinations to choose from. And that's all for today. It's a simple yet useful effect with a wide range of applications, so I hope you found this video at least somewhat interesting. There are multiple algorithms to create a similar dot matrix, and this one seemed quite easy to understand and implement to me. So take care and good luck with your projects, and see you in the next video.